lecture 29, where we continue study Taylor polynomials, but this time we want to see how these Taylor polynomials can be derived when applied to the composition of non-elementary functions. So let's suppose that a function f of x is expanded into a polynomial of degree less than or equal to n, Pn of x, plus little o of x to the n, and another function g of x is expanded into Qn of x plus little o of x to the n, both for x that goes to 0. So we are expanding f of x and g of x around the origin. Then we can say that the composition of f and g, so f of g of x, can be expanded into Pn of Qn of x plus little o of x to the n for x that goes to 0. However, this is valid if and only if g of 0 is equal to 0. That is, if Qn of x has no constant term. So this is the thing to remember. Now, the fact that g of 0 has to be equal to 0 is quite intuitive. If you think that we are now expanding the function f on g of x, and basically to apply Pn for the expansion of f, we need to have that the argument will go to 0 when x goes to 0. Okay, before moving to the proof of this theorem, let's familiarize with this with just an example. Okay, let's give this example. Let's suppose that we need to expand e raised to the sine of x up to n equal 4. Okay, now we need to use the expansion of e raised to the t, which we know is 1 plus t plus 1 divided by 2 t squared plus 1 divided by 6 t to the cube plus 1 divided by 24 t to the fourth plus little o of t to the fourth, right? So of course we stop the expansion at the power 4 just because this is what we are asked to do. We want to expand e to the sine of x up to the order 4. Now we need to replace t with sine of x, right? So we need to set t equal to sine of x, and this gives e raised to the sine of x equal to 1 plus sine of x plus 1/2 sine squared of x plus 1/6 sine cube of x plus 1 over 24 sine fourth of x plus little o of sine fourth of x. All right, And now, because we want to obtain a polynomial, we will expand sine of x, sine square of x, sine cube of x, and sine to the fourth of x. Okay, so this is just equal to 1 plus. We will replace sine of x with the expansion up to the order 4, which is x minus 1 over 6 x to the cube, and we know that this is the expansion up to the order 4 because all the even powers are missing. Then we have 1/2, and well, x minus 1/6 x to the cube plus little o of x to the fourth. Well, all this need to be raised to the second power. Plus, we have 1 over 6. Let me write this here. And we have once again x minus 1/6 x to the cube plus little o of x to the fourth. All this raised to the third power, plus 1 over 24 x minus 1/6 x to the cube plus little o of x to the fourth, all raised to the 4, plus little o of sine to the fourth of x. Okay? Now let's see. Because we need just to have the expansion up to the order 4, from developing all these terms, we get, well, 1, of course, it will remain exactly as it is. Then we have plus x minus 1/6 x to the cube. This remains exactly as it is, plus little o of x to the 4. And then we have plus 1/2. Now let's see what are the terms that remain after raising, developing the square. So we get x to the square, and now of course when we raise minus 1 over 6 x cubed to the square, we get x to the 6, which is something that will be eaten up by the infinitesimal of x to the 4. So the only thing that remains at this point is the double product, which is minus 1 over 3 x to the 4 plus little o of x to the 4. Right? And then let's move to the other term, which is 1 over 6. And the only thing that remains when trying to develop this cube, of course, is just x to the cube, right? Because all the other terms have a power larger than or equal to x to the fifth. So we just have 1/6 x to the cube plus little o of x to the fourth. And from the last one, of course, we just have 1 divided by 24 x to the 4 for the same reason, little o of x to the 4 plus little o of sine to the fourth of x. Okay, and let's see what kind of simplification we can do here. And well, of course we have 1 plus x, and we see that we can just cancel out minus 1/6 x to the cube with plus 1/6 x to the cube, right? and um, then we have plus 1/2 x squared. This of course remains, and then we have minus 1 over 6 x to the fourth plus 1 over 24 x to the fourth, and of course all the little o of x to the fourth by the properties of little o gets just into 1 little o of x to the 4 plus little o of sine to the fourth of x. Now, if we put together these two terms, what we get is 1 plus x plus 1/2 x to the square. Now, what we get here is simply 24, which is minus 4 plus 1. So this is becoming simply minus 1 over 8. So we can write simply minus 1 over 8 x to the 4 plus little o of x to the 4 plus little o of sine to the fourth of x. So this is the final result. Okay. What remains now to be seen is if we can encapsulate this little o of sine to the fourth of x into this little o of x to the fourth. Let's see if we can do this. So what I'm saying is that let me write little o of sine to the fourth of x. Well, this is little o of what? Well, we can write this as x to the fourth plus little o of x to the fourth. Let me explain this a little better, right? So we can write this as little o of what? We have sine of x, all this raised to the fourth. Now, if we expand sine of x, we have little o of x plus little o of x, all this raised to the fourth. Okay, but clearly when we develop the power, what we have is that the only thing that will remain is x to the fourth, and of course this will be little o of x to the fourth, right? Now, expanding this, we have little o of x to the fourth plus little o of x to the fourth. And by the properties of little o, we know that this is little o of x to the fourth plus little o of x to the fourth, which is little o of x to the fourth. So this will conclude the proof. Now, there are a few facts that can be generalized, okay? So we can have a generalization. General fact or facts. If we have little o of x to the n plus x to the m, I'm saying that this is simply little o of x to the n plus little o of x to the m. Okay, and let me give the proof of this fact. Proof. So this is the first result that we have, which we have indeed used in our previous proof. Okay. Well, little o of x to the n plus x to the m means omega of x times x to the n plus x to the m, right? Where omega of x is a function that goes to 0 when x goes to 0. But this is omega of x times x to the n plus omega of x times x to the m, right? But this is nothing else than the little o of x to the n, and this is little o of x to the m. So this concludes the proof of this first general fact. There is another fact that we have used, and the other fact is that if we have little o of x to the n, well, this is little o of x to the n. And let me prove this fact. Proof. The proof is the following. Little o of x to the n means omega of x times little o of x to the n, right? Where omega of x goes to 0. But this is like saying, instead of writing little o of x to the n, we can write omega 1 of x times x to the n. And we see now that this product is nothing else than some omega 2 of x that goes to 0. So we can rewrite this simply as little o of x to the n, which is what we wanted to prove. Now that we've got some familiarity with the theorem, let's prove the theorem itself. Before proving the theorem, let me just copy the statement of the theorem so that we can see exactly what we want to prove, right? So this is the theorem that refers to the composition of non-elementary functions. So we have a function f of x and a function g of x. We are making the composition of f and g, and we want to prove now that this composition can be expanded into a polynomial Pn of Qn of x plus little o of x of n. So let's start with the proof. And the proof is made into two steps. Okay, so first step is basically if we calculate f of g of x, okay, knowing that f of x is equal to Pn of x plus little o of x of n, and if we just replace x with g of x, what we get just by substitution is that this would be equal to Pn of g of x, right, plus little o of g of x, all this raised to the n. Okay, so this is just obtained by replacing x with the g of x. So the first thing that we want to prove is that little o of g of x, all raised to the n, is simply little o of x to the n, right? So this is what we want to prove. Okay, so to prove this, let's start from the simple definition. Little o of t to the n, we know that this is nothing else than omega t times t to the n with omega t that goes to 0 for t that goes to 0, right? And if we now just replace t equal to g of x, what we get? Well, we get that little o of g of x raised to the n, right? So this is equal to omega of g of x times g of x all raised to the n. All right? And now let me factor out an x to the n. Well, then we have g of x divided by x all raised to the n times omega of g of x. Now notice that this omega of g of x, this tends to 0 because we know that g of x tends to 0 when x goes to 0, and this is the meaning of this first condition. We said that when x goes to 0, g goes to 0. So if g goes to 0, omega of g of x of course goes to 0. Now the second thing we want to look at is this term that we got, this term here. Now this term, I say that this term is just a number. Let me prove this fact. Okay, let me prove this. I want to prove that g of x divided by x is just a number. Okay, now remember that g of x can be expanded into qn of x plus little o of x to the n, okay, by hypothesis. If we divide by x, we have g of x divided by x equal to qn of x divided by x plus little o of x to the n divided by x. But notice that when x goes to 0, of course this will go to 0 just by definition of little o of x to the n. So little o of x to the n is something that goes to 0 faster than x to the n, therefore it goes to 0 faster than x. So this second term is going to be equal to 0. And instead, if we divide the qn of x divided by x, what we get here is simply the coefficient of x in qn of x, because all the other terms will go to 0 when x goes to 0. So yes, this proves that g of x is just a number. Okay, so therefore we have, in conclusion, that let's rewrite what we just found. We found that the little o of g of x raised to the n is equal to a number, okay, number times omega of g of x times x to the n. But clearly, because this is just a number and omega of g of x goes to 0, this is something which we can call omega 1 of x that goes to 0, which proves, finally, that this entire thing is nothing else than little o of x to the n. And we are now ready to go to the step 2 of the proof. what we have just proved is that f of g of x is equal to, we said that this is Pn of g of x plus little o of x to the n. Okay, so the second thing we want to prove is that Pn of g of x is equal, we want to prove that this is equal to Pn of Qn of x plus, we could also assume that there will be some little o of x to the n that then will be encapsulated in the already present little o of x to the n. So this is our purpose. Now what we can do is just taking Pn of g of x and replace the expression of g of x. So this is equal to Pn of Qn of x plus little o of x to the n. All right, and well, but Pn, what is Pn? Well, Pn of t, let's say, this is a polynomial of degree less than or equal to n. Okay, so it will have a form like a0 plus a1t plus dot 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 an t to the n. So if we just replace t with Qn of x plus little o of x to the n, we have that Pn of Qn of x plus little o of x to the n is simply a0 plus a1 Qn of x plus little o of x to the n plus dot 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 an, and finally there will be Qn of x plus little o of x to the n, all raised to the n. Okay, but we can extract from every term just the Qn of x. So we have a0, this is the first term, remains exactly as it is, plus a1 Qn of x plus there will be some a2 and somewhere there will be Qn square of x plus dot 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 an times Qn of x all raised to the n. And all the other terms will include some little o of x to the n, so they can all of them can be encapsulated in a final little o of x to the n. But if you look at the first n plus 1 terms, these n plus 1 terms, this is nothing else that Pn evaluated at Qn of x, okay, that then will remain, and finally we have this little o of x to the n, and this will conclude the proof. Now that we have proved the theorem, let's apply this powerful result to this example 2, where we want to expand in Taylor polynomial the function cosine of sine of x and up to the order n equal 4 around the origin. And notice that we can do this just because sine of x goes to 0 for x that goes to 0, right? So this was the condition on the g function. Okay, in fact, you see that f of x in this case is just the cosine of x, and g of x is sine of x. Let's start by expanding the cosine of t up to the order 4. So we have 1 minus t squared divided by 2 plus t to the 4th divided by 24 plus little o of t to the 4th. And now by replacing t with sine of x, we get the cosine of sine of x is equal to 1 minus 1/2 sine square of x plus 1 divided by 24 sine to the 4th of x plus little o of sine to the 4th of x. Okay, so this is equal to 1 minus 1/2. We need to expand sine of x now. And sine of x will be expanded into x minus x to the cube divided by 6 plus little o of x to the 4th. This needs to be raised to the square, and then we have plus 1 over 24, and again we expand the sign into x minus x to the cube divided by 6 plus little o x to the 4th, all raised to the 4th power now. And we already proved that little o of sine to the 4th of x is little o of x to the 4th. So we have at this point 1 minus 1/2. Now clearly when we develop the square, we see that the only thing that will remain is x to the square minus 1/3 of x to the 4th, because all the other terms can be embodied into little o of x to the 4th. From the second term we have 1 over 24, and we're just left with x to the 4th, and clearly we have little o of x to the 4th. Now, just developing the product, we see that this is 1 minus 1/2 x squared plus 1/6 x to the 4th plus 1 over 24 x to the 4th plus little o of x to the 4th. And we can conclude this by, of course, just putting together these two terms, this term and this term, and what we get is again 1 minus 1/2 x squared. Well, this will become 5 divided by 24 x to the 4 plus little o of x to the 4th. And notice something, that indeed these can be also considered as little o of x to the 5th, because we know that this is a composition. Remember what we said when studying the composition of functions. Because cosine of x is an even function, well, then also the entire function cosine of sine of x is an even function, so it will only contains even powers of x. So the next term is going to be x to the 6th, so we can say that little o of x to the 4 can be replaced by little o of x to the 5. Now let's see if we can do the inverse. So example 3, can we expand sine of cosine of x up to n equal 4 around the origin? Well, the thing is that cosine of 0 is different from 0, so we cannot do the expansion around x not equal 0, okay? Just because one of the necessary conditions for the expansion of the compound function is missing. What we could do, so the alternative, so let me write that this cannot be expanded, but the alternative option is to expand sine of t around x naught equal 1. Okay, and when we will have this expansion, we will come back to this example. So it is clear at this point that we need to make practice with the Taylor expansions with the center different from the origin. So let's move to example 4, where we have f of x equal to e raised to the x. And we want to make an expansion around x naught equals 6. Now, first thing is evaluating the derivative of order k at 6, which is simply e to the 6. Okay, so this gives that e to the 6 is equal to, well, the function itself evaluated at 6, which is e to the 6, plus we have the first derivative evaluated at 6, which is again e to the 6 times x minus 6. Then we have 1/2. The second derivative evaluated at 6 again is e to the 6, and then we have x minus 6 raised to the square, and so on and so forth. So this is the expansion. Now there is another form of this. You remember that we also have introduced the increment h that is defined just as x minus 6. Of course, this implies that x can be expressed as h plus 6. All right? So we can now say that f of h, so this is the situation. We have this point 6, and we are trying to expand the function e to the x around this point, and we are using this h increment, which is the distance between 6 and x. Okay, so we can say that the function expanded around 6 becomes f of h equal to, which is now e to the h, right? So this is simply 1 plus h plus 1/2 h squared plus 1/6 h to the cube, and so on and so forth. And now, by just replacing h with x minus 6, we have 1 plus what we want to do now is we want to replace h with x minus 6, so we have f of x minus 6. This is now what? E to the x minus 6, which is e to the x times e to the minus 6, and this is equal to 1 plus x minus 6 plus 1/2 x minus 6 to the square plus 1/6 x minus 6 to the cube, and so on and so forth. Now, because we want to have e to the x, we need to multiply both sides by e to the 6, so that we get e to the 6 equal to e to the 6 plus e to the 6 times x minus 6 plus 1/2 e to the 6 x minus 6 square, and so on and so forth, and we have consistently the same result that we got before. Now, because we said in example 3 that we need the expansion of sine of x around x naught equal 1, let's move to this example 5, where we will expand the function f of x equal to sine of x around x naught equal 1. Alright, now we know that in the expansion we need to evaluate the function and the derivatives in 1. Okay, so let's start by f of x, which is by convention the derivative of order 0. Well, that implies that, okay, let me write down f of order 0 evaluated at x is sine of x, which implies that f of order 0 evaluated at 1 is sine of 1. 1 represents 1 radian. Then we have derivative of order 1 in x is the cosine of x, which implies that derivative of order 1 evaluated at 1 is the cosine of 1. Then derivative of order 2 in x is equal to minus sine of x, which gives derivative of order 2 in 1 equal to minus sine of 1. We know that we need to evaluate the first 4 derivatives because all the others repeat over and over again. So we have f of order 3 in x is equal to minus cosine of x, and this gives the derivative of order 3 in 1 is simply minus cosine of 1. Okay, so we are now ready. So let me call this first method. We can write now sine of x as the function evaluated at the point 1, which is sine of 1. Then we have the first derivative, which is sine of 1 times x minus 1. Then we have 1 over 2. We have the second derivative, which is minus sine of 1 times x minus 1 to the square, so on and so forth. Now, the second option would be to refer to the increment h, which is x minus 1, which implies, of course, that x is equal to 1 plus h, right? So, when evaluating sine of x, this would be just like writing sine of 1 plus h. And if we apply the formula for the addition, for the sum, we have sine of 1 times the cosine of h plus cosine of 1 times sine of h. And we can now expand cosine of h and sine of h, right? So this becomes sine of 1 times, well, the cosine of h is expanded into 1 minus h squared divided by 2 plus h to the 4 divided by 24, and so on and so forth, plus cosine of 1 that multiplies h minus h to the cube divided by 6 plus h to the 5th divided by 120, and so on and so forth. So this is the expansion of the sine around the point 1. And with this in mind, we can go back to example 3. Remember that in the example 3, we said that we wanted to expand the sine of cosine of x up to the order n equal 4, okay? And we needed the expansion of sine around 1, okay? So, and we will be using now one of the results that we just got in the previous example, and in particular we will be using this expression, okay? This gives the expansion of the sine function around the point 1. Okay, so sine of the cosine of x can be written as sine of, if we expand the cosine, we have 1 minus x squared divided by 2 plus x to the 4 divided by 24 plus little o of x to the 4th. And there is no point in considering other terms, because clearly we need to expand up to n equal 4. Now, notice that this can play the role of plus h. So we can now expand this expression by just using the previous expression, right? So, and this will become sine of 1 times what? Well, we have 1 minus h squared divided by 2, where h is now the previous expression that we have highlighted, plus h to the 4th divided by 24 plus dot dot dot, and then we have the cosine of 1 times h minus h to the cube divided by 6 plus h to the 5th divided by 120, and so on and so forth. Okay, so now we need to replace h with this expression. So what we have is sine of 1 times 1 minus 1 half. Well, we need to consider now h, which is minus x squared divided by 2 plus x to the 4th divided by 24 plus little o of x to the 4, all this squared, right? And then we need to take 1 over 24. We need to consider the same h, all raised to the 4th power plus little o of x to the 4th. Okay, so this is what this h is, again, minus x squared divided by 2 plus x to the 4th divided by 24 plus little o of x to the 4th, right? So this is nothing else that the parentheses that multiply sine of 1. Then we need to add the cosine of 1 that multiplies h, which is again minus x squared divided by 2 plus x to the 4th divided by 24 plus little o of x to the 4th, right, minus 1/6 of h, this time all raised to the 3rd. Sorry, this thing was something, we didn't need this. Okay, now I need to replace h in this expression, and once again we have minus x squared divided by 2 plus x to the 4 divided by 24 plus little o of x to the 4th, and of course there would be additional terms also here. Clearly there would be additional terms that we wouldn't consider, and here also additional terms that we won't consider. Now remember that we are asked to find an expansion up to the order 4. So we can immediately realize that all these terms are beyond the power of 4, because we start with the power of 8. And the same thing happens for this, so we can immediately remove this and all additional terms, so that we have this final expression, sine of 1 that multiplies 1, and we have minus 1/2. Let's see which term do we need to consider in this square. Well, the only term that will survive is x to the 4th divided by 4, because all additional terms have a power larger than 4. Okay, so we just need to consider little o of x to the 4 here. And the other term is cosine, and we have so plus cosine of 1 that multiplies now minus x squared divided by 2 plus x to the 4 divided by 24, okay, plus little o of x to the 4th. Right, so this is the final expression that can be also re-expressed as sine of 1 times 1, and we have minus 1/8 x to the 4th. Then we have plus the cosine of 1 that multiplies minus 1/2 x to the square plus 1 over 24 x to the 4th plus little o of x to the 4th. So this is the final expression. Another interesting example of expansion is the following example 6. Let's suppose we want to expand f of x equal to the logarithm of x. And remember what is the diagram of the logarithm. The logarithm is a function that is only defined for x larger than or equal to 0, and this point is 1. So clearly we cannot expand the logarithm around the origin because the function is only defined for x larger than 0. Let's try to expand the logarithm for x equals 7. Okay, so what we are trying to do now is basically finding an approximation of the logarithm with the polynomial function, which will do something like this. It will be a good approximation only in a neighborhood of 7. Okay, and we will consider this increment h. So we can right now, let's say that we want to take x naught equals 7, and we want to expand up to the order 4, and we will consider an increment x, which is simply 7 plus h. So the logarithm of 7 plus h, which will be the function itself evaluated at x, but x is now expressed as 7 plus h for h that goes to 0. So this logarithm can be also written as follows. Logarithm of, we can factor out 7 here, and we have 7 times 1 plus h divided by 7. And by the properties of the logarithm, we can express this as logarithm of 7 plus the logarithm of 1 plus h divided by 7. Okay, and now we recognize that what we would like to expand at this point is only the second term. Okay, so we can rewrite this as simply the logarithm of 7, which is just a constant, and by just applying the Taylor expansion of the logarithm of 1 plus x, we have simply h divided by 7 minus 1/2 h divided by 7 to the square plus 1 divided by 3 h divided by 7 to the cube minus 1 over 4 h divided by 7 to the 4th, and so on and so forth. Plus, so, or we can just stop here and consider little o of h. As a final example, let's try to solve the limit for x that goes to 0 of sine of x divided by x all raised to the 1 divided by the arc tangent square of x. And first thing, as always, let's try to replace x equals 0, and we see that when x goes to 0, sine of x divided by x of course tends to 1, and instead the arctangent tends to 0, so 1 over arctangent square tends to plus infinity, so we have an undeterminate form. Okay, so we need to devise a new method for solving the limit, and we know that whenever we have f of x raised to the g of x, we will resort to the exponential transformation, which works this way. We can rewrite sine of x on x all raised to the 1 divided by arc tangent square of x as e raised to the 1 divided by arc tangent square of x times the logarithm of sine of x divided by x. Okay, so we'll try now to solve this limit. And we still have an undetermined form, right? Because this exponent that we have here is for x that goes to 0, we have clearly infinity, because 1 over arc tangent square of x goes to infinity, times infinity. So we don't know exactly how this will work, right? So we would like to apply the Taylor polynomials, the expansions. Okay, so let's start by expanding sine of x. So remember that we are working around the origin, so what really counts is the low powers. So we might expand sine of x only to the x, but we want to be cautious, and we take also the other term, which is minus 1 over 6 x to the cube plus little o of x to the cube. And if we divide by x, we have that sine of x divided by x becomes 1 minus 1 over 6 x squared little o of x to the square. Okay, and now we need to take the logarithm of sine of x divided by x, right? So this becomes the logarithm of 1 minus 1 over 6 x squared plus little o of x squared. And well, what is this? This is h, right? Because for x that goes to 0, this will go to 0. So we can now reuse the usual formula that the logarithm of 1 plus h is equal to h plus little o of h. This is just the minimal term, the lowest power that we can assume. So we have this is equal to h, which is minus 1 over 6 x to the square plus little o of x to the square. And now we can evaluate the exponent of e, because the exponent will become 1 over arc tangent square of x times the logarithm of sine of x divided by x. Well, this, if we expand these terms, we have minus 1/6 x to the square plus little o of x to the square at the numerator, and the denominator is simply x squared plus little o of x to the square. And of course this tends to minus 1 over 6. So we can conclude that this limit is e raised to the minus 1 over 6.